whenever there. Okay, so we are recording and we are good to go, about 14 participants right now. So my name is Ari Alvarez. I will be filling in for Ken for a while. He may be back in some weeks. So one of the goals here is I provide make sure that you can meet every week and share all this information, and just doing the back end, trying to keep the recordings straight and post them in the YouTube, so you'll have everything on the links. I've been a Parallax customer since 1995. Started working for Parallax 1996, doing all the Spanish translations from Argentina. I was a Votech teacher there. Moved to Parallax and started working for Parallax 2002, and have been working on Parallax or Simplitronic, which is like a Parallax owned company since then. So it's 20 years. So right now filling up for Ken and just keep you going. My background was more education, not in the part of research and development at Parallax. So I do not know the new products over the last 10 years that much. I'm learning fast right now since I started here in Lachlan, California since Wednesday. So that being said, I'm really ready to, well, I need to mention that we are going to be running a sale. It actually is live right now. As you know, Ken has been showing you the updates on the P2EC Red B and the Red C, that we had a problem with the PCB panels. We are getting the replacements, hopefully arriving next week. So the problem is, all of you know the Red C is coming, so everybody stopped buying the Red Bs. So what we decided to do is run a sale. There's a sale right now on the Red B online. We are trying to clear the inventory. We even have purchase orders from some distributor somewhere, maybe it's one of you, on the Rev C specifically, and we do not have the pricing on the Rev C yet, but we put the Rev B on sale so we can clear all that inventory before we have the new boards. The idea is today we hand it over to Lachlan with an update on the P2 485, and then Chip will be bringing an update on the floating point. And the idea is to resolve some issues. When we end the presentation section, we will stop the recording, and then we will start the recording again for the discussion. So it will be 2 files. So when you go to the forum, instead of one link with a long video, it will be 2. And that will hopefully fix all the issues that we had. And I'm also trying to keep a list. If you have anything to present, or if you want to hear about something, for next week, we'll have the P2 documentation from Jeff, and a demo, specific demo from Lachlan on P2 485. And we will have Michael talking about another board that is in the pipeline that you already probably know about too. So that being said, I can hand it over to Lachlan for doing the presentation. So Lachlan, I cannot hear you. Let's see. There, I hear something now.
Yeah. Okay. My apologies. Despite testing this, I don't know, about 20 or 30 hours ago, I had to reboot urgently just before. Yeah, so today I want to talk about some testing we've been doing with RS485 industrial devices from the P2. It turns out you can actually talk to these devices directly from the P2 because the pin drive strength on the P2 is strong enough to comply with the RS485 driver requirements. So let me just, I've got to see if I can get this into the camera view here. So this is, you know, one example of a industrial RS485 module. These have been available for about 25 at least years. I've used them on previous jobs where you want to put a like a field device out in a electrical control cabinet somewhere, This particular one works with relays, has relays. However, you can get them for all sorts of serial conversion, to convert back to RS-232 at the end of maybe up to 4,000 feet of cable. So this is, obviously it has the kind of screw terminals and allows for, larger size wires, and runs from 24 volts DC. So it's suitable for use in industrial environments. And RS-45 is super common in industrial applications, including, almost all variable speed drives will talk it by default. So being able to just talk directly from the P2 to these devices is super useful. Let me just start up. I've got a presentation here. I just need to bring that up on screen and put that onto screen share. Can be a challenge. Let's find out why this isn't doing it.
Ari, do you need to stop sharing so he can share?
That's not me. Is that you?
It's just because I've rebooted and now I've lost. Okay, here we go. Oh no, you're right. Somebody else, Ari, you're right. You have to stop and then I can start.
Zoom. Stop.
There you go.
There you are.
Okay. Okay. So you can see that opening slide, okay? Yep, okay, great. Yeah, all right. So the trick, or the good thing about this, is that we only just need to use a few biasing resistors, like just some passive devices, in combination with the smart pins inside the P2, which enable a fairly simple implementation. The good thing about all this is that it'll work with any serial driver that we've already got. So this is just a technique or a layer on top of those other serial drivers which enable the communication. So just going back a little bit about RS-485, also known as, well, more recently described as EIA 485 in the specifications. It's a lot more robust than RS-232. You might use RS-232 around an office, but RS-485 is good for building sites or factories or electrical control cabinets. It's super reliable because it uses differential transmission lines, which of course are going on to being the kind of secret for everything, LVDS and HDMI and all these kind of things. It's typically used as a multi-drop network, which means you can have many nodes. And I think the specification is typically for up to 32 devices. But if you reduce the loading, you can go a lot further. And I think, get up towards 255 devices. It's also commonly spec'd for working up to 4,000 feet, cables. And one of the things I want to do in coming weeks on one of these other sessions is actually, just run it with a spool, like a long spool of cable, 300 feet kind of box of Cat5 cable, just to kind of demonstrate. Yeah, and as previously discussed, super widely used. Couple of devices which, one of the industrial module on the left there we'll work with today. That's in the Advantic relay module. And on the right-hand side is just a cheap, you can buy these from eBay or even DigiKey for, of the order of $10, USB to 485 converter, and we'll use that in our demonstration next time. So the key requirements for RS-485 are to be able to drive at least 1.5 volts into a 54 ohm load. So 54 ohm load is kind of, it's effectively a resistor at the driving end and a resistor at the other end of the very long line. You typically have about 100 ohms to 120 ohms terminating resistors at each end. And so when you put those two in parallel, you've got around, 50 or 60 ohms. And so the specification calls for being able to drive at least 1.5 volts into 50 ohms. What that implies is you need, on a 3.3 volt microcontroller, you need to have drive FETs which are less than 32 ohms on the upper and the lower side. So the P1 can probably do this. It's right. It's kind of on the borderline at around 30 ohms. So that's the requirement on the driving side. And I've included down in the bottom right-hand side, there's a very good document from TI, which I've included the reference there for, a training document on RS-485, and that just describes or shows, your switches and your transistors inside your either driver or microcontroller in this case, and what they're doing. And they're basically reversing the polarity of nodes A and B. So from positive to negative, and so you need to be able to switch each node both directions, to pull it high or low depending on what you're trying to send. The other requirement which is in the specification is that you need to be able to deal with a common mode voltage difference of -7 to +12 volts, and that won't be met by what we're doing with the P2. So that's a noise immunity. Like if you imagine you've got a 4,000 feet line, then you can have quite a voltage difference between one end of your building site and the other. So we won't be able to meet that requirement. It might go something like -1 or 2 volts up to maybe 5 or 6 or thereabouts. But this isn't really an issue for a lot of, like, if you're doing bench testing or if you're in a local control panel and you just want to talk to a variable speed drive, it's not really an issue. It's just if you wanted to claim any kind of formal compliance, then this isn't the thing for you, and you're better off just buying a compliant driver chip. But having said that, this is still super useful for all sorts of testing and getting up and running, and smaller installations and setups. So smart pins to the rescue. This is making use, or this technique here, we're using a couple of tricks with the smart pins, or a couple of features of the smart pins. The first feature is that you can use the TT setup bits in the pin configuration to mirror a neighboring pin, mirror and invert, in our case, a neighboring pin. So what we're doing in this case, we're using P0 and P1 to do the transmission. And P0 is I guess what you call normally the positive. It looks like a normal serial cable, serial signal when you look at it on a crow. And using the TT bits on smart pin P1, we're able to copy and invert the status of P0. The benefit of doing it this way is just that all we're doing is setting up the smart pin mode, and for the rest of the setup, we can just use whatever preferred serial method. If you're used to using FTS, or you can also bit bang, like not bit bang, but use the smart pin async IO transmission mode, like we're doing in this demo here. So with RS-485, the bus is normally idle. Obviously, you can have up to 32 nodes on there typically, and so you just want the bus to just sit biased but idle. And what we're setting up is to float the pins when there's no data to be transmitted, and then as soon as there is data to transmit, you assert and you kind of flip that resistor, those termination resistors. You want to flip the voltage on those by driving strongly from the P2. To put the data onto the bus. Okay. So probably just going back a step, are there any questions about that much so far before we kind of get into the demo and we can see things actually running? No? Okay, we'll get into the demo and then we can come back to how we calculate and get things organized. So just in the demo, it's a very last minute photo here of the setup here, but you'll notice, like on the graphic at the bottom left, you'll see there's a little plug-in board we've got on the P2 eval board. that's got 5 resistors which bias the line in total. The middle horizontal resistor, which we've got the crow probes hooked onto, that is the termination resistor. So in this case, it's 100 ohms. We have down below that a couple of tan or brown colored resistors. They're pulling that termination resistor to the rail. So they're the kind of biasing resistors. And then at the top, like above that, closest to the P2 eval, there's 2 resistors connected in series with P0 and P1. Okay, and that's what's doing all the work here. So you can see the 2 crow probes which are hooked onto the termination resistor, which are your nodes A and B. And just off screen, you can't really see, but down in the bottom left corner, there's a blue and an orange wire which hook the nodes A and B of the RS-45 together. Now, what I'm going to try and do is swap over to a crow screen, which we can hopefully connect live onto. Let's zoom in somehow. I might have to momentarily stop sharing, and so I can choose a different video source. Okay, so hopefully you can see the crow screen now live. This is Brian. This belongs to Brian. This crow. It's a slightly different beast in that it's a different brand, but it has a nice feature in that it's got a VGA connector output, and that enables us to hook onto a VGA to HDMI converter and then convert that into a webcam signal, and eventually you get it so it comes into the PC. So what we're doing at the moment is we're transmitting a command to turn the relays on from Propeller tool, from the P2, and then 3 seconds later we're sending another command to turn the relays off. Now there are 2 traces on the screen. The top one, the yellow colored trace, corresponds to P0, pin P0, and it's what I was saying was kind of your conventional kind of serial signal where you've got the resting or idling high, and then when you transmit the data, it pulls that node down. The 2 levels we're dealing with here, we've set up for about 450 millivolts of differential transmission, and that means we've put it symmetric around the P2's 1.65 volt threshold. And so the high and low voltages in real terms are 1.4 and 1.9 volts. And I've just to make things simpler, I've moved I've offset the 2 levels. But in real life, they're actually, if I put them at the same potential, this is what it actually looks like if you're looking at the voltages. And so, yeah, you've got the differential things which are inverted relative to each other. At the moment, the relay module isn't energized. I haven't put the 24 volts power to the industrial module, but what I'm going to do next is just turn that on, and you'll see that come online, and you'll see the response from that, and hopefully you'll probably also hear the relay clicking. So I'm turning that on now. It takes about 3 or 5 seconds to boot up. And okay, so you can see now over on the right hand side of the crow that we've got a response coming back from the RS-45 module, and it's more strong, I guess, than the drive signal from the P2 because it's a compliant RS-45 driver. However, given that the P2 just switches at 1.65 volts in the middle of those 2 signals, it doesn't really matter whether it's that strong or not. We're not dealing with a lot of noise. I'm not sure if you can hear the relay clicking, but here I've got a lamp hooked up to the relay, which I'll show you in a moment. And yeah, so that's the thing in action. And I'll switch back to camera now. So while we're on the crow, are there any questions about that signal? Where basically we're sending a command which is around 6 or 7 bytes long in that signal stream. And if you look at the vertical grid line around the middle of the screen, you'll just see there's 1 byte which transfers between sending a 0 and sending a hex F, which tell the relays to all turn on or all turn off. And the rest of the setup is just setting the command and the address of what node we're talking to. The response from the module on the right-hand side, it comes back with a greater than sign and then a CR, like a carriage return to say I've received and acknowledged and executed the command. Okay, so here's our, I'll just bring this into screenshot and hopefully not break the transmission. So we've got this is the lead of the week. It's something we got cheap from the local hardware shop that are clearing these out. These are like some kind of strange festoon lamp kind of thing, which they plug into some kind of party LED kind of system. But nicely, they operate off 30 volts DC, and so they're good for just plugging in and working with industrial systems. So yeah, that's the that's pretty much the demo, and the connection's dodgy. Oh, that wasn't the P2.
Hey Lachlan, what color is that light to you? It shows up as pink to us, but
yeah, I'd say it's pink. It's kind of interesting because when it's off, you'll see it's like looks orange almost when it starts up. They sell these. This is what they're clearing out at the local hardware shop this week. This is what it is. They're at Bunnings. They used to be like $11 a pack, and now they're like $1 a pack, and you get like 5 of them, so you can have different colors. There's a blue one, so it's kind of. It's, as I said, it's the lead of the week. It's what I'm saying to my friends. Hey, these are clearing out cheap. Do you want to use those? So, so that's pretty much the demo. So, are there any questions at that point, like about the demo and that running? Is that all kind of clear how that operates?
I just had a thought. In a factory, there's a lot of potential for ground loops that are all over the place, and so you need to use some kind of differential signaling. But this thing could probably be refashioned to use some sort of a signaling method where it's always, it's always AC as long as data is going, and so that and then maybe use some kinds of transformers at either end. There are probably some cheap transformers, like probably 10 base T or something, but it'd be neat to have that thing signaling over transformers so that there could be real isolation and escape from local grounds.
Yeah, so there are certainly the reference I gave before, that TI training document on RS-45 is really good, and it goes into some of these issues and how you can break some loops just by having some extra resistors, etc. But they sort of list and sell what TI's got a pretty decent range of Maxim and others have good ranges of isolators and proper driving stuff, including higher immunity. Some of the industrial networks like Siemens Profibus or Profibus, depending on where you are in the world, they use a similar kind of scheme, based on 5-volt 5-volt setup. Are they similar kind of bias resistors, but they have a little bit more margin. There are sort of more, like if the normal -7 to +12 volt range isn't enough, there are some devices which allow more. So there's certainly, I guess this sort of lays the fundamentals of something that works pretty well for most applications, but you can go to the other extremes of it and get, additional protection or greater speeds. So just on the speed thing, I haven't mentioned that in the presentation, but this works super fast. We had this on a different crow which doesn't hook up, but that other crow decodes the serial up to 20 megabits per second, and it was working all the way up there, and the waveforms beyond that after it stopped decoding still looked really good, you know, up at 30 or 40 megabits per second. And you know, so it's a good technique. And you know, eventually the aim with this is to go on and drive other devices like LCDs and things, you know, in a sort of differential LVDS kind of style, or a synthetic LVDS style. And you know, it isn't really an industrial replacement, or, you know, you can't really substitute this, but it does give you a kind of a cheap way of getting up and running fast. And then, you know, for some applications, it'll be fine. And then, you know, if you're selling a product into industry, you probably do want the real HDMI transmitter, or you know, transceiver, like RS-485 transceiver. But for a lot of, you know, for getting up and running fast, it kind of demonstrates the P2's flexibility. And the other thing is, because you've got this on every pin, you know, you can have like 32 sets of RS-485 transmitters very easily. And if you wanted to take that further, you could almost like Charlie plex the RS-485 transmitters and have different modes and things. So, you know, you can imagine if you got a kind of a star network or something, this would be really super flexible and easy to get up and running.
Hey, Lachlan, we had Jim asking if you can share the protection schematic, the pin protection schematic again.
Yeah, I've got some hand-drawn slides here, which we'll move on to next, and we'll go through the kind of theory in the background and the pin protection. Now I need to get back to the screen sharing again. Okay, so resistor calculations for Jim, and like just the general theory with this. It's probably easy actually to see, like I've got it there, but it's rotated. Where we start from is like you want to set up a voltage swing of around 450 millivolts roundabout, you know, give or take. At the receiver end, they need at least 200 millivolts, and so that gives you some kind of margin. The implication of that, if you want that kind of swing and we want to put it around the midpoint, it means our nodes A and B, like the transmission nodes A and B, you want those around 1.4 and 1.9 volts, like we saw on the Crow waveforms. The starting point is really setting up the termination, like the termination resistor. You want those to be set up to match whatever cable medium characteristic impedance you've got. So typically for a Cat5 cable, that's around 100 ohms. And you know, for some other, like the old twisted pair kind of multi-pair cables, might be a little bit higher, maybe 120 ohms. So that basically dictates what termination resistor you're going to set up there. And if you want a signal swing of around 450 millivolts, and that implies you're going to have around you know, 4.5 milliamps of bias current running through that resistor. So that's kind of the starting point. Once you've got that, you work out, okay, well, how do we bias that? You know, what resistors do we need to bias that in a bus, in a resting network? And that involves calculating that pull-up resistor and the pull-down resistor, which, you know, calculate out to 280 ohms. So you'd use 270 ohm resistors for that. And that's quite similar to like a lot of, you see a lot of diagrams showing, you know, a few hundred ohms of termination resistance on Profi bus plugs or other biasing schemes. One advantage of having that biasing scheme in a resting network means, because you're pulling the A line high and the B line low at rest, you can also detect cases of like shorts between A and B, and if the A and B lines get shorted out to ground individually, then you can detect that in the driver. You know, you could easily write code to check for that in the P2. So that's the second stage to calculate those pull-up resistors. And then once you've got those, this is the final stage, like working out the pin protection resistors. So inside the P2, what you're trying to do is you're trying to flip the voltage on this termination resistor. And that involves you basically pulling that upper node to ground and you're pulling the lower node up to the 3.3 volts. And if you run the calculations of what kind of resistance you need, you come out with around 120 ohms needed. And inside the P2, these internal P2 resistors are around 19 ohms each. The P2 is pretty strong on drive, you know, that's kind of almost FPGA levels of signal drive. And so that you end up with an external resistance of around 100 ohms to achieve what you want to do. In answering, you know, what Jim was asking, one of the things you've got now is if you've got these resistors sort of protecting the P2 or coming back that way, a signal driven externally, sorry, from this side, so a signal driven externally coming back at the P2 effectively goes through a resistive divider, a differential sort of resistive divider. And so that's why I was saying, you know, you do get a little bit of negative voltage protection, you know, if you're sending signals in here, because this divider sends most of that signal to the rails. Yeah, that's, you know, so having 100 ohms in series, you can trade this off a little bit. You could have a stronger drive. You could actually omit those resistors completely if you're just worried about transmitting strongly. You then get less protection on the receiving side, you know, so it's a trade-off. Yeah, but it can be messed around with a little bit, you know. And likewise, you could actually use the DACs to bias the lines if you wanted to on the P2, and you could omit, you know, you might not need the pull up and pull down resistor. So you could simplify this, you know, with the P2. You've got a lot of flexibility there, but I just wanted to present something which is kind of a reasonable starting point for it all, and then we can mess with it from there if need be. Okay. So the questions about that calculation, those values, is that kind of straightforward? Yeah. Okay.
Hey, Lachlan, I have a question. I don't know, you might have mentioned it, but maybe I didn't hear it, but are you using the differential input mode to read these signals coming back?
Probably next week. in the coming weeks, yeah. At the moment, we're just transmitting. We're making sure we've got a signal coming back, but we haven't done the kind of turnaround to receive that signal. One thing, we did start off with a different biasing condition, so we just moved that bias recently up to being around the midpoint to make it easier to you know, to use the smart pins, and that means we don't necessarily need the comparator mode to do that. You know, that'll make it more straightforward to work with existing objects. So yeah, in the next session when we have that, probably the week after next, Jeff will talk at next week about the documentation, P2 documentation, and then maybe the week after that, or whenever we next get back onto this, we can present, you know, receiving like the other direction, and completing the round trip communication.
Okay, yeah. If I recall, if you have 100 millivolts differential signal, I believe that's good for like 30 megahertz. But yeah, if you can get like, you know, a whole 1 volt of differential, you can go maybe 50 or 60 megahertz on that comparator. Okay.
Yeah, I remember some of that testing as well, and you're right. Yeah, it kind of gets internally attenuated down, but you're right. If you start with a big swing, and on the driving side, the P2 obviously, you know, it's good for driving video fast, and so it's good. As I said, we on the Crow, it looked good, you know, up into the 30 to 50 kind of megahertz range on with these resistors, and that's kind of where I was hoping to get to for driving LCDs and things. You know, that gives us some hope that it might just work, even though it's only sort of resistive loading. So yeah, but you're right. You could trade off, you know, the signal swing and push the boundaries. It'll be interesting to see where this gets to, because a lot of those industrial, like those fast driving chips and things, I think as Jim might have linked to in the chat, you know, they do maybe 20 megahertz or 20 megabits per second, or maybe some of them do 50 megabits per second. And you know, we might be able to kind of get near some of those speeds. I'm not sure. I need to find a kind of a test device which you can use to try it at those kind of speeds, because I doubt that little RS-45 transmitter to USB will be able to keep up. But yeah, I'll maybe talk to Jim and see if he knows of anything we could use to test at the higher speeds.
Yeah, good. And this the whole point of this kind of controlled impedance topology is to be able to push signals over very long distances, right?
Yep.
Without them becoming distorted.
Yeah, yeah. Yeah, and there's other sides to it, you know, around the power, you know, the power required to do it. You know, if you just oscillating or just swinging over a small range, you can both go fast, but you're also relatively power efficient to do it. You know, versus loading and unloading. You know, you've got to move a lot of charge around if you're trying to load up a heavy capacitive cable, you know, to lift it up and down. So yeah, it's a good system, and it's obviously it sort of underpins a whole lot of more modern kind of communication systems. So that's why, you know, that little board we've made up's got the 4 channels, you know, so we can drive multi-channel things like similar to HDMI and LVDS, and see how we go. And you know, we might have to tune and change resistors and things along the way, but yeah, it's a good scheme, and we're grateful, Chip, for putting in the you know, that differential drive mode and things into the smart pins where it can just clone its neighbor. That makes it kind of easy and flexible, and separates out the, you know, the hardware and software requirements. So it's good. Yeah.
Looks great. That would make a really nice app note. I mean, I know a lot of companies have done these kinds of things for their chips, but when you get to the point where you have some software that makes it all go, talk to Ari or Ken, and it would be neat to turn this into one of these quick bite things.
Yeah, that's right. Because it's really, what we're describing here is really just a technique for how to do this easily. So that there's no real object for this. I mean, we can kind of create an object artificially, which say talks to these Advantic or Atom modules. You know, in some ways to actually have some kind of tangible placeholder for what, you know, what's being demonstrated here. But really, this technique can just be applied to pretty much any other, you know, bit of code. You know, so it's really just, you know, the key thing to it is really just setting up the smart pins in the right way that makes it easy to, you know, to do whatever you like on the software side. So really, we just got to think about, okay, what does this enable and what can we demonstrate? And so in coming weeks, we'll talk to industrial like variable speed drives, which are almost invariably, you know, have RS-45 communication ports on them. And in the forums, there was a person who was using RS-45 kind of encoders, you know, that were putting out a differential RS-45 kind of pulse, and they were using like a conversion chip to convert it back to sort of TTL or CMOS kind of levels. But with this setup, you'd probably be fine, you know, unless your encoder is super fast, which I suspect, you know, this would outrun even the fastest encoders. Then you might not need those kind of receiver chips and things which exist. There's still arguments, you know, if you're building a product and selling it, then you're probably still going to want, you know, the formal compliance. But you know, this will take a long way towards that anyway. So
that's good.
Yeah. Okay, so this is yeah. So in the coming weeks, what we'll talk about, like, this is a surprisingly well-made temperature probe, which comes from, you can actually buy these from DigiKey. It's another one of these cases. So it's this is got a little, looks like a Sensign or similar kind of sensor on the end there for sensing temperature and humidity. It's got a brass environmental filter at the top there, which screws on. It's really nicely made with anodized aluminium, you know, and unscrews, and it's got some features on the inside. Now, unfortunately, the data sheet's in Chinese, and we're working on that. But you know, one way or another, we'll get this up and running. These are around $25 roughly on DigiKey, I think, for a pretty nice quality sensor. And so we've got obviously this little RS-45 converter for USB, which will enable us to kind of spy on the network. So the PC can just be another node on the network, so you can see the data going in and out. We'll also hook up to variable speed drives like we're talking about before. And possibly, if we can get our hands on them, maybe some of those RS-45 encoders that we've seen on the forums recently. And then ultimately, where we're going with this, we want to also hook up to LCDs, which talk LVDS, and which is kind of quite related to what we're doing here. You know, they just operate with slightly different swings, and obviously they need to drive fast. But the question is, how fast can we go with this? So we'll try and speed it up and improve the layout and to see where we can get to. So I think this will probably take 4 or 5 kind of sessions where we'll just bite off a little bit at a time and see where we end up. That's almost it from me. There's just a couple of things I was going to say. We're working on a couple of different boards. We're working on a lot of boards at the moment, but these, I'm going to send some of these over to Jim, and and some to Parallax, I guess. And so these are just little differential breakout, like generic differential breakout boards. We've got like a surface mount version and the one we're using here, which has got through-hole resistors, which makes it a little bit easy just to change values. Both of them drive 4 channels off a single P2 eval head, header, I should say. We've got a couple of other products we're working on. We've got a product called the Kentosaurus at this stage. This has a P2 underneath, but on the top of the module, it's actually got headers for it's got 4 of the P2 eval headers on the top on a compact module, so it doesn't have the full complement, but it manages to squeeze like a double header here and a double header there. And so if you want to just add like a hyper-RAM or something on, then that'll be possible. Compact size, and Kentosaurus, because it's got a whole lot of spikes, like when the thing's assembled, it ends up with a whole heap of spikes on it. We've got a what's now up to the 4th revision of a what we call the Babel board. So this plugs into a dual header, and we break out to a whole heap of signals. You can depending on what headers you solder into this, you can plug in an Arduino board, a cheap LCD, servos, Digilent PMOD, including double Digilent PMODs. You can set also 2 microbus click modules on there, using a sort of a slightly, 8 lines per microbus, which is slightly different to the Parallax breakout board. But the other thing you can do on this, you can also put a stepper motor driver in between the servo pins. So standard, servo driver like used everywhere in 3D printers and things, and it just breaks out along the bottom to a larger size screw terminal to enable you to easily connect up stepper motors. So that's another product we're working on. We've also got a display project we're working on, and we're getting a bit of progress on the SparkFun micromod style P2 board. It needs a mechanical revision, but otherwise it looks like that's all going to work as well. So yeah, we'll talk about that in coming months, and put some content together around what we're doing with those. So yeah, that's about it, I think.
Thank you, Lachlan.
Yeah, thanks, Lachlan.
No problem. Yeah.
So Chip, you're up.
All right, let's see. Okay, let me start the screen share here. Let's see, is anyone sharing? It says someone is sharing.
Yeah, that's me. I've got to bring it back and
My internet is so poor here. It may cut out a few times. Just bear with me. I have a nice low res presentation. Okay,
can't get out of this. Oh, here we go. Up here. Right, stop.
there we go. Okay. All right, let's see here. Portion of screen. All right, here we go. Come on. Okay, so can you guys see my little peanut thing here?
Yeah.
Okay, so these are the things I've implemented so far. We have the conversions between float and integer, between float and integer. And then we have the, what do you call these? The relational operators, and then just the basic math operators. We have negate, absolute, square root, and then the plus, minus, multiply, divide. I'm thinking, just as I was getting ready here, I was thinking that this NAND instruction is runtime only. I really can't think of a case where it would need to be compile time due to some kind of problem that might crop up in a con block where you're operating on some floating point numbers. So it's a runtime only thing. Okay, so we have the very basics here. Now, I'm still alive here. I'll go down here. So to review, this is what the floating point format looks like, right? We've got a sign bit and then 8 bits for the exponent, which are kind of like somewhat inconveniently placed so that you have to shift by 1 to get to that whole byte. And then there's a 23-bit mantissa that has an implied leading 1, except for denormalized numbers, which become very small. Then the mantissa is the number, but we have to wind it up when we unpack it, and then do the opposite when we pack it back into this format. So here I have some code here. I just have this so that we can do debug. And I have a thing here that we assign I to 1.0 and we look at it. And then we take the square root of that and we look at it. And then we do some floating point operation and then we look at that, right? So let's 3F8 and then all zeros, that's 1 in floating point. So we run this thing. We can see here the first one reports 3F80, that's 1. Then when we take the square root of it, that's 1, right? And then we multiply it by 2 and add 2 to it. So that would make it 4. So this last value here, 4080, that's actually 4 in floating point. So this stuff is all working. It's debugged. I mean, there's order of operation in these kinds of things. I did not implement something like this, so you could say like I plus dot equals 1.0. We could do that, and there's really only 4 operators that would need that treatment. But then it opens a box of maybe we need to do that for lots more. So the way I have this thing set up now, it's just very straightforward. You just do assignments. These things have to work, within. Well, we have a right hand and we have a left hand assignment, and we use this operator to assign the results. So it doesn't have all these implied modifiers like we have for integers. I think because floating point is something special, and it's I don't know if we want to dress up and kind of, what would it cloud up the language with all these arcane little symbolic, not even symbols, they're like these little character operators. So I think if for now anyway, we just leave it with these, right? But we do have order of operation, which applies, of course, to unaries, and then here are the binary operations. So multiply, divide have the same precedence, which is higher than add and subtract. So this allows you to construct simple, floating point calculations. The trick is though, and I didn't remember this, when I was just writing this code to show you guys, I did this, right? Which of course, It looks like it's kind of almost there, but it's not, because to treat these values as floating point, we need to remember to put the dot after the operators, right? And then it all works fine. And if you want to say like -1 here, you'd have to say minus, right? Now, if we run this, this is BF80 is -1, but then when we take the square root of -1, that generates this value, which is within the range of the not a number values, right? This is not a number because the exponent is at the maximum and the mantissa is non-zero. So the code is sensitive to that. When you do a NaN instruction, it just looks for what matters. It doesn't look for FF, just that you've got a maximum exponent and a non-zero mantissa. So anyway, see here, once we get this NaN thing going, it's kind of clingy, and everything that's done with NaN thereafter is kind of polluted, and it just inherits the NaN status, the not a number status. So what I'm adding now, you can see here, we're just using this uhex, and just so we can look at the hex, but I have something called FP. I was thinking I could call it maybe float, but that just looks kind of weird. I thought of doing this, but that might be okay. But then if we ever did any other IEEE thing, that might not be appropriate, because what we really have is IEEE 754. You guys have any input on what you'd like to see these as? Am I still connected? I don't even know that my connection's still working.
Yeah, it's still working.
Okay, all right. So would FP be a good for floating point right here? Do you think that would be appropriate for debug to print the, you know, because
keep it simple.
Okay, well, FP
Maybe-
is per,
Maybe FPDEC, FPDEC or something, sort of like UDEC. Yeah,
or how about just like floating point decimal? That's
or FDEC, yeah. Because we
because
might
everything
eventually,
else. Go ahead.
you might also, for some debugging purposes, want to do an F hex. I don't know about that, but in C you can print floating
Yeah,
point
maybe F,
base 16, but FDEC seems good.
yeah. Yeah, because we have SDEC and UDEC for signed decimal, unsigned decimal. FDEC is nice because it's 4 letters, and every one of these things is a 4-letter word. So that just keeps it consistent. All right, so that's the next thing. And what I was going to do is just kind of constrain it. So it'll print up to like 10 to the 9th or 10 to the -9th in direct form, but it will revert to scientific notation if you get to like beyond ±10 for the exponent. Does that sound agreeable? By the way, Eric Smith's compiler already has floating point. Eric, how did you do this like operator dot thing?
Well, I haven't done it in Spin.
You've added it to Spin too already, right?
No, I haven't. It's just in C and Basic.
Okay. All right, so it's still a little open then.
Yep.
Okay. All right, it's a little open then, which is good. But Eric's compiler in C and Basic supports floating point with a whole host of operations. Quite a few more than I have at the moment. But I set up, I've got the basics in place now. I could start adding sine, cosine, these kinds of things.
Or you might want to just make an object for sine, cosine, and things like that. I mean, they don't have to be part of the language. I think we lost Chip.
Yeah, I don't see Chip. Let me see. Signal was getting worse.
Need some advertisements you can run, Ari, during the chip mob.
Yeah, he's back.
Here we go. He's back.
You are back, Chip, but you are in mute. Let me see if I can. No, she's
Okay, sorry about that.
there.
Okay, I'm back.
So Chip, I was suggesting that you don't have to do the trig functions in the language. You can make them an object or something.
Yes, yeah, no, it could be that way. I'm thinking though that it really doesn't take much because we have the Cordic in hardware to do sine, cosine, log, exponent. I don't think it would take that much code. I mean, we added about 0.7 kilobytes to the interpreter, I believe, to add this floating point stuff in so far. And I don't have any number printing in the interpreter, but I'm going to have that in the debug display. So it wouldn't be that expensive just to add like an F sine and F cosine for float, because I've kind of got all the nomenclature set up so that if it's floating point, it just begins with F.
Yeah, I mean, you could, but again, you know, why drag it around for the people who aren't using it?
Yeah.
And well, I mean, either way, you can see. Have you got my floating point object from the OBX?
Yeah, I have it open in one of my. It's the one you sent me.
Yeah.
Yes, it's open in one of these. What is this thing called? Sublime. This text editor that I have.
Okay, that's fine. I'm just gonna say
called,
that
this is it, right? Binfloat.spin2.
Yeah, I think that's it. So that's got a bunch of the trig functions in there. And
yes. Yeah, this is a bit, you got like, wow, you got it all here. And this, I was looking at this is like overwhelming. You got everything here. And it's a lot of code, a lot of spin2 code. This is all work, right?
this all, it's been tested. The power ones are a little bit off for my IEEE. If you run the test program, there's a few failures, but for log and power.
But they're just LSB type issues, right?
Some are more than one LSB. Some are like two.
Okay. Well, you know, if you use the Cordic to do things like log and exponent, it's solving to 32-bit precision, right? Well, no, actually,
no.
Uses 5 bits, so it's 27 bits of mantissa.
Yeah, but it falls away really quickly when you go away from, like, it's great for integers and things that are close to 1 and 0.
Right.
Actually, I shouldn't say that. It's a fixed point basically, right? So it's great in a certain range, but it falls off really quickly when you get near extreme values. Like,
right, when there's a point at which it's all 1-to-1, both directions, but at some point it starts to fall apart because you don't have enough effective mantissa bits to go both directions anymore.
Right, exactly.
But it gets, I remember tweaking it and coming up with these like really fine little, you know, super sub LSB tweaking values when I was developing it that I put in to make it go as far as it got. But couldn't you kind of deal with that? Can't we deal with that in software where we take away the potential for high exponents when we do the actual
well, no, because you've only got 5 bits for the exponent, whereas the floating point
Right.
numbers have 8 bits. So,
Yeah, and then it always converts from the MSBs down, right?
yeah. So for some of the trig functions and for the exponent and log, I had to do some hacking, and with the log and power, I am using the Cordic, but it does fall apart on some extreme
Yeah, yeah,
values.
okay. But yeah, I've been kind of looking at this as sort of a basis for like, okay, what all should I be thinking to do? You got a really nice set of functions here. Actually, this is, let's see here, let me move this up. This is it, right? This is your whole set from here to here.
Yeah, I think so. There might be a few
Okay.
up above. Don't know.
Oh, well, yeah, there are some things like
There's some
conversions
conversion.
between float.
Yeah.
Yeah. Okay, well, yeah, this is kind of what I've been looking at as a reference for what I should consider to add, but you know, since once I get the debug printing out floating point numbers, I think there's going to be some desire for the graphical debug displays to be able to handle floating point then, right? Because when people have floating point data, they're going to want to look at it. They're going to want to be able to run it through the scope and whatnot, right?
Yes. Somewhere. Okay, this might be a little bit old. There's I do have functions that'll use send to send floating point to convert to and from strings.
Oh, okay. All right. So I was just getting into that, and that's complicated.
That's nasty. Yeah.
I was dividing, or I was multiplying the 8-bit exponent by 77, and I thought that's got to have some log relationship. So 77 over 256 is like 0.301, which is very close to the log of 2, right?
Right.
So that's how we have to scale. We have to take the, to figure out what decimal exponent we need to convert the base 2 exponent to a number to look up the base 10. What would we call it? It's how we can take the manticipits and then print them out. I was looking at some of my old code that did that. So that's kind of the next big thing I got to do, is relearn how that works.
I think I ended up using a table.
Yeah, like what? Yes, for all the powers of 10, right? From minus
Yeah.
34 to plus 34, or minus 38 to plus 38.
Okay, I forgot to document them, but I think they're probably in your file. There's a send float method that streams
Here we go.
using send.
Let's see. I think this is part of it anyway. Yeah, send float.
Yeah, it is. So
Yeah.
it just divides, pulls out. I'm not sure how accurate this one is actually.
Yeah, here's the table. This is the table. So
Yeah.
the power of 10 table. So minus 45 to 39, 10 to the 39. Oh, that's minus 45. Oh, those are for denormalized.
Right.
Oh, you know, I don't think I did that. I'll have to experiment with that. I only went to like 39, I think. That's 39. Yeah, I was thinking it would have been nice to have done what you were talking about, where we use like 10 million, you know, normalize the manticid of 10 million so that we get 7 digits.
Yeah, for printing and converting to and from ASCII, it's much easier. Yeah.
Oh yeah, because this, I have to get into granny gear and I have to, it takes me a couple days to reabsorb how all this stuff works before I can do much with it. It's a real kind of a pain.
Yeah. Yeah, it is.
But I've already got all the tools oriented towards IEEE 754. And so if I were to do the base, the 10 million normalized to 1, I'd have to, there's too much history at this point to change it all.
Fair enough.
Yeah. So I figured on the debug screens that the scope would need it, the XY scope would need it, the FFT would need it, and the spectroscope would need it, and that's it. Because the rest are more binary type things, like the bitmap and the MIDI and that stuff, logic analyzer. So I'd have to put some float sensitivity. But anytime I convey a float, it's either going to have a decimal in it or it's going to have the letter E in it. Just say we have an exponent coming. All right, well, let's see. I'll stop sharing this. That kind of concludes where I'm at. Ari, you're still there, right? There you are.
All right, yes, yeah.
Okay. Hey, does anyone have any questions about floating point that I'm working on? Or that Eric's worked on?
One little one. Hello?
Wait, say that again, Enrique?
One little question only. There are any hints into the representation that enable you to fast converting numbers that are well within the integer, so you can spot as fast as possible that it was an integer that was converted to a floating point? That exist into the representation. Is there any hints that enable you to spot fast that the number you are dealing is exactly one integer that has been converted from integer to floating point? Or no, there are not any hints that enable you. You have a hint for the NAM stuff. You can fast spot that a number is a NAM. Okay, a number, right. No. A representation is a NAM. There are any other hints that enable your routines to fastly spot that one or both of the operators you are dealing at the moment are simply integer numbers that were converted to floating point, or no, you just need to step by step doing all the operations?
Yeah, are you asking, like, is there any key within the data pattern that would let us know if it's a float, so we know what kind of operation to use?
Not exactly kind of operation, but if I convert 1 to floating point, it is different than if I had 0.9999999 any times up to the limit of the representation, right?
Oh, well, let's just see. Yeah, let's just do it real quick here. Let me pull this thing up.
Well, actually, that table we're looking at right now shows a bunch of integers.
You mean this one in blue?
The one with the powers of 10 table, yeah, shows a whole bunch of integers. So you can see there's not really much of a pattern.
Yeah, it's crazy. We'll even do it here. We'll say, let's say, okay, we have 1.0. We'll print that, and then here we'll say 0.1234567. We should be able to get
That's
7.
probably, I wouldn't be sure that's going to be different.
All right. Well, yeah, it might round up. So we'll say unsigned hex. Oh yeah, look, it is. It's barely under. It's like 1. It's like it. Let's see, what did it do? It decremented the exponent and set all of the bits in the mantissa.
I asked that because I was for a long time I was programming programmable calculators in my life for the early times, and you can write spot in the early times even if we had 26 bits of mantissa and 2 for exponent. You can really do fast spots where you are dealing with integer numbers that were converted during the calculations, and when you are dealing with fully floating points, because they are a little hints into the representation that a human being can use to spot. But I'm asking because I want to avoid that nasty bug of raising the square root of 2 to a power of 2 and don't getting back 2. That is a nice bug from HP, I remember, at the time of the Apollo mission, that leads to wrong calculations because people doesn't yet understand how to avoid such kind of bugs.
Yeah. You mean you'd start with 2 and do something that should come back to 2, but it would come back with 2.0000.
Yes,
something.
and when you calculate the trajectory, it's at 500 miles per hour, rapidly it will go off track because you have a lot of errors being committed along the calculations that could be avoided. Some of the errors are due to you have a bad interpretation of the problem. So there is a lot of talk about that in the forums, that people doesn't really understand what they are doing. And most of the time they can do the same thing with integers without relying on floating points. But sometimes you need a floating point badly, but you need to rely on it at least within the limits of the representation you have in the hardware you are using or in the software you are using.
Well,
yeah.
There is a standard, the IEEE 32 standard that specifies this floating point format, also specifies the behavior of all the operations and how things should be rounded and all that sort of thing. And I think Chip is probably trying to come as close as he can to that standard.
Well, look, you know let's look at this. If we have a 24-bit mantissa, right? That's 2 to the 24th. So here is our, and now we want to take the log of this, and this will tell us how many digits are in that thing, right? So 7.22 digits. That's what we should expect. So here we have 1, 2, 3, 4, 5, 6, 7, and then 0.2. Well, I guess there's some kind of knee in there that's a little bumpy as we run through different types of numbers. But look at this. If I run this thing here, it comes out 3F7FFFFF, right? But if we just add one more little, nudge it up just a tad, it becomes 1.0.
Yeah. So the short answer to your question, Enrique, is no. There's no the format, as you can see, is just a binary floating point. So it's not really obvious to a human which things come from what. I mean, if you use it a lot, looking at the hex, you can eventually get a feeling of if the exponent's small and there's a lot of zeros at the bottom of the mantissa, you can kind of guess it came from an integer, but it's not part of the format.
Okay.
Right.
Anything that's
Okay.
a power of 2 should work out properly, like because it is 2 to the x. Powers of 2 are great in this format, but powers of 10 are not. Like 0.1
Right, yeah,
can't
powers
be
of,
represented.
yeah, powers of 2 will always have all 0 bits in the exponent. Like if we say, let's, a nice big number is 65536, right? That's 2 to the 16th. And we get 4, 7, 8. And those are all exponent bits. And then the mantissa is all 0. And then if we add a half to that, then we're going to get a 4. We're going to get C in that one digit. Or no, maybe it just incremented it. What was that value? Oh, no, there it is. How did it wind up? Oh, because, oh, yeah. We would have had to say, I didn't mean that. I meant 65536 plus 32768. What's that? We go like this. Now this will be, oh, whoops. Put this thing in the wrong place. Okay, so that's 1.5 of 2 to the 16th. So then now it's 47C. It was 478. So we've added basically a big power of 2 plus half of plus the next lower power of 2 to give us an LSB. And then we could go like 16, 384, 8192, 4096, 2048, and so on. And then we start filling in more of those bits. Now we've got FC.
Yeah. Okay. I
Alright.
got it. I got it.
Yeah, let me just, one more thing. We could go like this. There we go. Yeah, so there we have, but see, it's just a binary number tracking where's the MSB position at in power of 2 terms. But see those bits, that 7F underscore FF, those are the LSBs of that binary number there. But yeah, the base 10 numbers become really impossible for a human to interpret by looking at the pattern. Ari.
All right. Well, thank you, Chip, for the presentation. So that will
But
then-
Ari, I want to say something.
Yep.
Okay, yeah, that's all I've got. But maybe if you want, it might be interesting to tell everybody like what you've been doing for the past, how many years has it been? And what how dynamics have changed with China and these kinds of things. These guys might find it interesting.
Okay, well, let me end just a second. I want to make sure that we record all of these, the presentation section, and I will start recording again. So just give me a second.